well, what about all the stuff that's like not dark matter, like gases
dust
and stuff like that, and dust?
Gas. Yep. So that is it basically it just complicates it. It's not the killer to this thing, but it complicates it. So I mean, just thinking right off the bat, you might think, okay, then obviously we're going to miss matter because there's dust there that we aren't having to account for. But it turns out that dust actually blocks some of the light, so then that would actually have the reverse effect. So this is all taken into account, and there's different ways. I mean, basically the real way it's taken into account is through quantum mechanics. So we're not looking at the whole spectrum of light, right? But we're looking at specific quantum lines. And so a quantum line that doesn't interact with the dust, because that energy won't get absorbed by the dust, you can look at that one and you can compare it to a quantum line that does interact with the dust, and then you can see how much dust is there by how much it's revolving from that one that it does interact.
Right.
So, does that make sense?
Okay.
But yeah, I mean, it's a great question because that has to be taken into account, but it just complicates the things, but the basic idea is that scaling.
And then like more massive stars emitting more light, how do they figure all that stuff out?
That you do in our galaxy. So that physicists are getting really good at now. So we look at a specific star in our galaxy and we can see the mass, because say it's a binary star system, so we can see them orbiting. We can determine the mass of the stars, and then we can look at the amount of light coming, and we know that a heavier star will, basically just the fusion reactions going on at the core of the star, cause it to emit more light. But that kind of scale is on like you're talking about factors of 2, 3, 4, 5 up to 10. Versus like dark matter scales, we're talking about like orders of magnitude, like 10 to the 3, 10 to the 5 sometimes, stuff like that.
Yeah.
It's a much bigger effect.
Okay.
Any other questions on gravitational lensing? So those are the three major lines of evidence that have convinced astrophysicists, or most astrophysicists, that there's dark matter in our universe and that there's a lot of it, and it's prevalent throughout the universe. And hopefully I've convinced you a bit that that's real. Okay, so like I said, the three main lines: galaxy clusters, velocity rotation curves, and Einstein rings. Okay, so I have no idea why it's doing that, but the dark matter candidates. So the number one proposed explanation for dark matter is neutralinos. So neutralinos are just a theoretically predicted class of supersymmetric particles. Basically, they're something that theorists have come up with that we think would not interact with light, and that you could therefore. Okay, so it explains dark matter because it would not interact with light, but it would have a lot of mass. Okay, the supersymmetric particle is sometimes abbreviated to SUSY, so you may hear about that in the media, and like Ben was talking about earlier, the Tevatron, the Large Hadron Collider at CERN, are looking for supersymmetric particles right now. They've never been observed before, but they're predicted by a lot of theories now. And the number one that we think is for dark matter is weakly interacting massive particles, or WIMPs for short. So it's just literally like the name says, the massive particles, they gravitationally interact weakly. That's one line of evidence. That's what most astrophysicists currently think is the explanation for dark matter, and the search is on for them right now. Another line is machos. Literally, it's named to go directly against WIMPs, physicists being creative in the naming scheme. And I have no idea what's doing that. So machos are massive astrophysical compact halo objects. That's the abbreviation, and it was named again for machos. I'm trying to see if I can remember these points. So it's the kind of thing like if like a brown star, for example, is something that is it's out there and it's an astrophysical object. It gravitationally interacts, but it emits very little light. So this is thought it's perhaps these things that could be scattered throughout the galaxy, and this is what corresponds to this matter that can't be seen. And so actually machos is reality too, and there's some of these things, but it turns out that they cannot account for all the dark matter, all these effects that we've observed. So definitely machos, possibly a lot, but it's still not enough to explain all the dark matter effects. And then,
What's a weakly interacting massive particle?
It is a neutrino or SUSY particle, or basically it's some type of particle that has mass, so it interacts gravitationally, but not electromagnetically. So the term that we use is baryonic. Baryonic corresponds to stable 3-quark state. Basically means it will interact with light. Weakly interacting massive particle is just a proposed type of particle. It's a name given to something that doesn't interact with light but does interact with mass.
Okay.
Yeah?
It's basically a synonym for dark matter,
Yes.
but it's, you know,
This
this is small dark matter, and Montauk's are big dark matter.
Yeah.
That's the main difference.
Modified Newtonian dynamics is the third explanation for dark matter that has been proposed. So the way this goes is basically Newton's laws are adjusted at small accelerations. So I said earlier, Newton proposed that the force is equal to the mass, the inertial mass times acceleration. And people have proposed that, well, perhaps there's more terms later on that have only effect at very small accelerations. This is an interesting way to go about it, but there's a lot of problems with this one. Starting with it hasn't been extended to relativity yet, so there's no relativistic modified Newtonian dynamics. It's called MOND for short. And another thing is that the work they're doing right now is a lot of times they'll explain one observational effect of dark matter, but it skews a lot of other gravitationally known facts. So it's interesting, but at this point it still needs a lot of work. So like I said a minute ago, the neutralinos, the WIMPs, are generally accepted as what will be the explanation for dark matter. Any questions on that? Cool. So next is the scope of dark matter. So the Wilkinson Microwave Anisotropy Probe, WMAP for short, was a NASA mission satellite launched about just over a decade ago now. And it went up there and measured the density of the cosmic microwave background. So I mean, we could talk for hours about the cosmic microwave background, but the basic idea is that right after that we think the universe started from a Big Bang. So it was a highly dense state in its initial time. So this corresponded to a black body where there's all kinds of photons moving around in the universe. And they were scattering all around as they were interacting with this dense matter. And then basically all at one instant, like bam, the universe was transparent to these photons now, and it happened homogeneously throughout the universe. And so we see these photons now coming toward us from every direction in the sky. It's always coming, they're prevalent throughout the universe. And this effect is called the cosmic microwave background. So there's a lot you can do with this stuff. The cosmic microwave background is the reason why we know our universe is accelerating now as opposed to decelerating, and a lot of things have come up with it. But one of the things, or the thing that's most prevalent to this talk, is that they used it to measure the energy densities in the universe, so specifically the matter. So what they found was that there's 5 times more dark matter than regular matter. And basically, ordinary atoms, or the stuff I call baryonic matter, is about 4.6% of our universe, of our observable universe. Dark matter is up to 23.3%, so almost 30% is matter, and the rest is made up of radiation and something that's thought to be called dark energy or cosmological constant. Almost the entire 70% of the rest is the cosmological constant. But the point is that dark matter, there's a ton of this stuff out there. So like, if you can imagine everything that we've done with matter right now, if dark matter was that rich a substance, like, just think about where technology will go, what we're going to do with it. And obviously it can explain a lot of things. So this is why physicists really want to figure out what this stuff is. And dark energy is nobody's working on that yet because it's so far off our books. This is a good picture of what WMAP found for the cosmic microwave background. So that's our horizon. That's everything we can see in our universe. And the background is extremely homogeneous. Like, it's very consistent throughout the whole background. So, which is good. That makes sense. But only small perturbations in that result in things like galaxy formation and star formation, stuff like that. So what they've plotted here is the very small perturbations. So this kind of color scale is on the order of like 1 in 10 to the 5.